Here we are going to do the share screen. Okay, so today we can finish the BST, the binary search tree, the last method that we are going to implement about delete. So before we go to the code, I will do a quick review about the delete operation in binary search tree. Okay, so that later on when we read the code, we still have some idea. So let's first take a look at the tree that we discussed yesterday. So we have this left tree down, and then the right tree is J, and then we have A here, and we have E here, and we have C here. C here, and we have B and D here, D here, and then we have H here, we have O here, and then we have I here. Say waiting room, admit. I here, and then we have M here, and P here, and KN, and then we have L. Okay. Admit all, okay. And K and L. Okay, so let's see the tree. And for our delete operation, because for binary search tree, the search and the insert, it's quite straightforward, is it? And yesterday we also discussed traversing. And for traversing, we discussed three traversing: in order, pre-order, and post-order, is it? And they all involve recursive concept. And the delete is a little bit of comprehensive, okay? So generally speaking, we divide them into three cases. The first case is leaf node. You delete a leaf node. You find the leaf node, you delete. That's quite straightforward. You just find it and delete it, is it? And the second case is node only has one branch. Okay, so the case that we discuss is like node E, is it? If you want to delete it, is it? And that's also not too comprehensive, is it? Because it only has one branch. So you connect its parents, is it, with its child, that's the only branch. So that's the second case. And the third case is node has both branch. Node has both branches. That's a little bit of comprehensive, is it? So suppose we want to get node J deleted, is it? If you just delete, there is no way to just connect, is it? So the idea to do that is you do in order traversing, is it? Find its in order successor. The direct in order successor, is it? And in order, we know that in order, if you do the in order visit, it will be in ascending order, is it? So by the tree, yesterday we discussed the in order, you just follow the right branch and all the way go the left, is it? And the K, is it? Is the in order successor, is it? So this node is the in order successor. So what we are going to do is you find the in order successor. So that's the first step, is it? And the second step is you swap. Is it? Swap node J and K, is it? in this case. So, okay, I'm going to put K here. And then I'm going to put J here. Let's put J here. And after this, then I reduce the case. So case reduced to, in this case, reduced to case 2, is it? Case 2. So the node has one branch, is it? And if the node has one branch, we know then it's quite simple. You just can reconnect the parent node and the child node, is it? So that's how the delete operation works. So the algorithm that we discussed. And then next, let's go ahead and take a look at the coding part about delete. Okay. So the delete is you are going to delete some item. Okay, delete some item. And in this case, because we have 3 cases we need to deal, is it? So that's why you also need to know who the parent node is if you find the node, is it? And over here, because you remember yesterday we discussed that search to function, is it? That search to method search some item, is it? And at the same time, it will tell you where the node itself is it? So the node, the location of the node, and at the same time, the parent of the node, is it? So in our case, there is that node J, is it? And it's a parent node, is it? So, or like node E, and it's a parent node, is it? So that's, we also want to keep track of, is it? To keep track of the node itself and its parent node. And in our search to, how do we achieve that? Through a bin node array, is that bin node array? And we just reassign it to location, the parent for our coding, so that is a name. Based on the name, it's easy for us to write the code, is it? And then we just go ahead, determine different scenarios, is it? And in the scenarios, so this is the case for if the node has both branches. If the node you're going to delete, so this is a case 3, okay? The node has both branches. And if the node has both branches, and we just discussed, is it, in regarding that node J's case, is it? So node J is here. So that's our node J, is it? Then you go to its right, is it? So this is the location. This is our location node J, is it? Then you go to its right, is it? Because we need to find the in order successor. It's next in order successor, is it? Okay, and at the same time, we also keep track of where the parent node is it? And you go to the right, is it? That's what, and what we do. And then we go to the left, is it? So that's why you see you keep going to the left, is it? Keep going to the left. Okay, and at the same time, you update the parent node. Okay, update the parent node. And once you reach, because where you're going to reach, is it? You're going to reach until what? Until there is some dead end you reach, is it? Then the loop is going to be stopped. The loop stopped, and what you did? You're going to swap, is it? That's what we did. So in our case, is node K here, is it? Here is node K, and node K can have some other tree, is it? And then you are going to swap this two. But just swap what? Swap the contents, is it? So J change to K, is it? And K change to J, updated to J, is it? So we swap the contents. Okay, swap the contents, and then you reduce the code, is it? Reduce the case to the single node case, or no or leaf node case, is it? And at the same time, you also keep track of where the node is. You're going to do the delete, is it? You relocate it, basically, is it? And then you relocate, and then you're going to do delete, is it? Going to do delete, how do we do the delete? Is we are going to reconnect, is it? Reconnect the node with the parent node, is it? With the parent node. And you need to, because you're going to delete that node, is it? So you also need to know its child node, is it? So in our case, so here is, we already swapped, is it? We already swapped. So basically now this is J, is it? And J will have some single branch, is it? Have single branch. So you're going to determine the single branch. So this is the child, because you need to find where the child node is it? So you need to find the child node, is it? Find the child node, okay, and this is a special case. Okay, this special case is in case it's the root node. Is it? If the root node has two branch, how are we going to do? Then you need to update the root node. Is it? So that's why you need to let the root node point. So that's take that special case, and then you're going to reconnect parent with the child node. Is it? So in our case over here, it's so you have this, and then go all the way to the left, is it? So here is our J, is it? And this is its children's node, is it? But over here, that's the parent node. And then this is the child, is it? You're going to delete it, is it? So that's why you just reset it. Okay, reset it based on its branch. It belongs to who, is it? Okay, so that's the coding part regarding regarding the delete. Okay, delete. And the in order, pre-order, we already discussed. Okay, post order. And what's the next interesting thing? And also quite useful is, we call it level order. Okay, level order. So what does the level order mean? So the concept is kind of like this. Suppose we have that tree, is it? Like in this case, it's F, and over here is J, is it? That's our previous tree, is it? And over here we have node A. And over here we have node E, is it? And something else, okay. Node J over here we have H. Over here we have O, is it? And then we have I. Is it something like this? So what does the level order mean? Okay, level order is previously when we do in order or pre-order or post-order, is it something like it's just by, it's always follow the tree, is it a certain branch? So level order means you want to level by level. You want your output going to look like the tree level, is it? So this is root level, is it? This is the next level, is it? Ideally, the binary search tree, grows. So the tree also has depths, is it? So this is the tree's depths, is it? Depths. Is it from the root node all the way to the leaf node? Is it? In this case, you have 1, 2, 3, 4. We have 4 levels, is it? Including the root level, is it? And ideally, if it's a completely balanced tree, is it? Then how many nodes you should have at each level, is it? So at root level, it should be 2 to the 0. We call level 0, is it? It's 1 node. At the second level, is it? It's 2 to the 1. So it's 2 nodes, is it? At the next one, ideally, you should also have something here, is it? Then if you count, it's 1, 2, 3, 4, is it? And 3, 4 is what? It's 2 to the 2, is it? So it's level 0, level 1, level 2, then it's 2 to the 2, so it's 4, is it? And if perfectly balanced over here, you should have, is it? Over here, you should have, and over here, you should have, is it? Then it's what? It's 2 to the 3, is it? So it's what? It's 8, is it? So if it's case level, is it? But over here, count from 0, okay, 0 to the case level. Then it should what? Should 2 to the key nodes. Is it at each level? Is it? So the tree, the whole tree, the nodes growth is by 2 to the k. Is it? And if you want to count totally how many nodes in the tree, then it should what? It should be 1 plus 2 plus 2 to the 2. Is it something like this? Is it? Okay, so it's some math sequence. Is it the total number of tree? In case it's perfect tree. Okay, here I mean a perfectly balanced tree. Okay, it's something like this. That's why we also see when you have the binary search tree, is it? When you do search, the search involved, the comparison is just log 2n. If total number of this is a number of nodes. Is it? So it should be log 2, is it? So the time is quite efficient, is it? So that's why we see binary search tree. It's very efficient for you to do the search. Okay, so we understand what the concept of level order is. The level order is, okay. And here we can also see how do we achieve this. We use some concept we already learned before. We use some queue, okay, to keep track of, okay, where you already visited level by level. So we have a queue here, is it? And initially your queue will just have the root node. So you have a queue, is it? You just have root node in your queue, is it? And then we are going to have a loop, is it? We are going to have the loop, and the loop is through the queue, okay? And let's see. And it first find the queue size. So in this case, the size is 1, is it? So it's going to loop from 0 to 1, is it? Not including 1. So basically just do 1 iteration, is it? So you get this node out, is it? You get this root node out, is it? So it's, in our case, it's going to be node G, is it? Node G going to be out, is it? And then you print it, is it? I print it out, is it? But at the same time, what I'm going to do, you're going to add its left and right, is it? Left is F and right is J, is it? So F is going to be added, J is going to be added, is it? Into the queue, is it? Okay, so this for loop, is it? Just take care of whatever you get out from the queue, is it? And you print it, and then you add that nodes left and right, is it, to the queue, is it? So that's what this part did. Okay, let's just try to save some space so that we can take a clear look of the whole coding. And so let's just go back to our tree, okay, to see how this works. So we have that F, and then we have the J, is it? We don't have this part. We have A here, is it? And then you have H here. You have O here, is it? So we just see the root already out, is it? We already add what? We add the roots left and right, is it? So it's F and J, is it? We add it, is it? We added, and then we output what here? You output G, is it? At the same time, you output a new line, is it? So it will move to the next line. And then you go back to the loop through your queue, is it? Okay, this time it's what? It's you get your queues front, so F is going to be out, and you print it, is it? But at the same time, you're going to add its left and right to the queue, is it? So its left doesn't have anything, the right is what? It's A, is it? So A is going to be added, is it? Oh, at the same, oh no, I'm sorry, it should be output here, F, is it? So it's going to be added here, is it? But it's not a stop because this time your queue size what? Previous or before we add, the size is what? Before we add A, the size is 2, is it? Size is 2, and then I add A here, is it? Size is 2, okay, I already loop one time, is it? Then I should look my second time, then I get J here, is it? Get J output, is it? And then you add the J's left and right, is it? J's left and right, it's H and O, is it? H and O in the queue, is it? And then you print a line, is it? So the second level finished. Oh, where is it? The second level is finished. The first level is finished. Is it? Then we moved. Then we move to the third level. Is it third level? The third level, then what you first are going to do is you need to find the queue size. Is the queue size what? In this case, it's 3. Is it? And then it's going to do the same thing for each node. Is it? Will get it and add it to the queue. So through this way, you see, if we use queue also, is it combined with the tree, then we can also achieve the level by level visit. Okay, so this is just some other interesting thing. Okay, and generally speaking, like of those concepts that we discussed for the binary search tree, and for a lot of job interview, what I know is they test you like this kind of like a level traversal. Okay, how do you do this? So this kind of algorithm. Okay, so we so it's going to be helpful. So in summary, if you are interested, there are a lot of things you can do around binary search tree. Okay, but the basic concept we already discussed. Okay, so you can find more exercise to try to do that. So here the key concept is we already see is regarding binary search tree. If we want to do some algorithm, is it you can do recursive a lot. So it involves recursive, is it a lot? Or you can combine it, is it with other data structure, is it? Other ADT, is it abstract data structure? Is it other data structure? In this case, it's Q, is it? And achieve a lot of your goals. Okay, so that's the part for binary search tree. We are done. And what is the next part I'm going to start is another quite useful concept, okay, regarding binary search tree application, okay. It's called Hoffman code. And in computer science, there are all sorts of coding mechanisms, approaches, okay, very smart way, okay. And you will see this is one of the smart way, okay. And even like our cell phone, is it the cellular signal, is it? It's called CDMA, okay. It's called the division multiple access. It's also by how do we, so all of the concept is all sorts of coding. It is so like a Hoffman. So this is can be used for compression, because in computer science, is it like how do you do image compression? Is it so all of those kind of concept? Is it over here? Then it involves certain coding mechanism. Is it? But those CDS, this is signal code. Is there signal code? And it also involves some kind of mechanism, quite very comprehensive. Okay, and there are some other coding like error detection and error correction, especially for cybersecurity. Is it error detection, correction? There are also all sorts of coding scheme, okay, but let's see here, this is purely like you can use the coding algorithm to do compression, okay, and the compression, there are some other ways to do compression. Is it like a JPEG? Is it, and those are not the pure raw the coding. Okay, let's see. The Hoffman coding. Okay, so what's the concept? Hoffman coding. Okay, and right now, because we all use digital, is it before the digital before the digital age, a lot of time, I'm not sure if you heard like a telegraph, is it? So telegraph, it's also used a certain coding scheme. Okay, so Hoffman coding is one of the coding scheme. And so let's see, the idea is kind of like this. So suppose you have a huge document. Is it some huge document? Is it, and you wanted to compress it? Is it, or there are some other meaningful, some other thing you want to deal with it? And then document anyway, it's all letters, is it? So certain letters. And for each of the letter, it has the occurrence. Is it in your document? Is it? So a lot of time we can collect the frequency. Is it the frequency of the letter's occurrence? And then we can encode it. Is it? So that's kind of the idea of the coding scheme. So what that means, suppose over here, okay, I have some letters, it looks like this. Is it? I have letter B. Okay, letter B, its frequency, it's 10%. And then I have letter C. Is it letter C, its frequency is also 10%. And we have letter D, the percentage is 0.15, okay? And we also have what? Letter A, it's 0.2, okay? And we have letter E, its frequency is 0.45, is it? So all of those numbers are just the frequency, okay, of each of the letters, suppose occurred in some document, And then what over here, we are going to use some coding scheme, is it? And for each of the letter, if you use ASCII code or Unicode, is it Unicoding? ASCII code, it's 7 digit, it's 7 bits. Is it is 7 bits, and basically you use 8 bits. Generally speaking, we said like each character is it's 1 byte. Is it 1 byte? But generally speaking, it's some number from 0 to 127. Is it? So this is 2 to the 8. Is it? So that's ASCII code. Is it? And the Unicode, it's 16 bits. It's a 16 bits. So then in all of these cases, is it ASCII or Unicode? And each of the letter, when you do code using binary means either 0 or 1. Is it either 0 or 1? Then you either need 8 bits, is it? Or you need 16 bits. Is it? Even though that letter may only appear once in your document, but you still need 16 bits to store it. Is it? So, so then it's kind of take a lot of space. Is it? So the idea for Hoffman coding is we are not going to use, so all of this consider fixed length. Fixed length of code. Is it? And Hoffman, it's variable length. variable length of code. Okay, so then I'm going to use 0 and 1 to code those letters, but it doesn't need to be all the same number of digits. Maybe B can be like, in this case, B can be 4 bits, and E, maybe I just use 1 bit. Okay, so some kind of mechanism like this, okay? So that's the background. Then let's see, how do we achieve this? Is it, so generally speaking, you are going to first sort a frequency in ascending order. Okay, so what we are going to do is I have B over here. Is it? It appears 0, 1. And then I have C, it appears 0, 1, is it? And then I have D, D appears 0.15, is it? Then I have what? I have A, A appears 0.2, okay? And then I have E, E's occurrence is 0.45, is it? I arrange them in ascending order, is it? And then I'm going to do bottom up building tree. So this is different from binary search tree. The binary search tree, you start with root node. It's up to bottom. Is it? You from root all the way to the leaf. Is it? Over here it's different. I'm going to bottom up. So what I'm going to do, okay, so I have this two. This two, what's its? I'm going to add their frequency together. So it's going to be 0, 2, is it? And then I'm going to have the 2 branches out of this number, is it? And then next I'm going to add 0, 2 with D, is it? So, oh no, so it's going to be like this. I add a node. So that node is going 0.35, is it? Okay, and then next I'm going to add 0.35 with 0, 2. So it's going to be what? 0.55. Is it? 0.55. And then next I'm going to add what? Add 0. With the last one, so it's going to be 1.0. Oh, 1.0. Is it? I'm going to have like this kind of, so it's also a tree-like. Is it also a tree-like? But it doesn't, this tree not a binary search tree, okay? It's not left less than root than node and right greater than node. No, it doesn't have that kind of characteristic, okay? You just build from the bottom up, okay, of this tree. And then what we are going to do is starting from the root node. Is it? If the branch is left, I assign it to 0. The branch, if it's go to left, it's 0. It's 0. It's 0. Okay. And if the branch is right, I assign to 1. And if the branch is right, assign to 1. If the branch is right, I assign to 1. If the branch is right, I assign to 1. Okay. So I have this tree that in each of the branch, and I also represent as 0 and 1. Is it? And then I will have the code for each of the letter. Okay, so for letter B, is it? For letter B, how do you find the letter? Okay, from root and all the way follow the left branch, you find B. And go through each branch, you find the number. Is it 0, 0, then 0, then 0? Is it? Okay, you finish, you find B, is it? And then let's see C. For C, how do you go to the C? From root, so 0, 0, 0, and 1, is it? So 0, 0, 0, 1, is it? And then let's see D. Okay, for D, it's going to do what? 0, 0, 1, is it? Okay, so D is going 0, 0, 1, is it? And then what? And then A, is it? A is what? A is 0, 1, is it? A is 0, 1, is it? And you find what? Find E, is it? E is what? E is 1, is it? So then all of these binary digits, is it? Binary digit, is it? Those are called Hoffman code. Hoffman code. Okay, for the corresponding letter. Okay, for the corresponding letter. But of course, this is not general. It's just regarding this special document. Okay, and width of the letter's appearance frequency, you record it like this, then you can build its corresponding Hoffman tree, and then you can encode all of the letters like this. Is it? So if you compare this with our ASCII or Unicode, it's the number of digits is much fewer. Is it? And if you take a look, then you will find the most frequent. So most frequent letter, is it? Most frequent letter, then what? Then it's a Hoffman code. It's a Hoffman code. It's what? It's shorter. Is it? It's shorter. And if it's least frequency, is it like B? Then it's a Hoffman code. Length is longer. Is it? And this makes sense, is it? Because the most frequent you use the shorter, then it will take fewer space, is it? So that's why we see this is variable length encoding scheme, is it? And it can achieve the goal to do the compression, is it? Okay, so this is the idea of Hoffman coding, and we call the tree we just built, is it? We can call it a double tree. It's not a binary search tree, okay? It's called double tree. And double tree, and we build it bottom up, okay? So this is the idea about Hoffman and Hoffman codings, how it comes from, okay? So the key point is Hoffman codes. Hoffman codes. It has two features, okay? Variable length. So variable length of codes. Okay, and we just explained, is it? And the most frequent, so the more frequent the letter is it? And the code length is shorter. Is shorter, is it? So that's the first feature. The second feature, there is another important feature is your Hoffman code must also meet what we call it immediately decodable. Immediately decodable, okay, immediately decodable. So what is this idea? The idea is, suppose you assign character and it's coding like this. You assign A as 0, 1. So this is your letter, is it? And this is your code. Okay, and then you assign it as 1, 0, 0, 0, is it? And C, suppose you assign it as 1, 0, 1, 0, is it? And D, you assign it as 1, 0. And then E, you assign it as 0, versus what we previously discussed. Then this is not immediately decodable. This doesn't meet that. Why? Letter E, its code is 0. Letter A, its prefix is also 0. Is it? Then in this case, it will cause confusion. Is it? So immediately decodable means one letter's code cannot be prefix of other letters code. Okay, it cannot, because if it is, then suppose you have something like this, 0, 1, is it? And when, later on we will see our applications. And when you read this, so is this part of the code or it's just itself? Is it? So it will cause confusion, is it? So the code you provide that must also meet the immediately decodable rule, okay? When you check if your Hoffman code is a valid one. So that's the concept, okay? And next, let's see, how do we like to build the Hoffman tree? Is it Hoffman tree? So generally speaking, is like we have the code file. Okay, so what the code file will look like is it will have character and its code. And its code. Is it? Suppose it looks like this. Okay, so you have B 0, 0, 0, 0. Is it? And then I have C is 0, 0, 0, 1. Okay, and D, then I have 0, 0, 1. Okay. And A is going to be 0, 1, okay? And the E is going to be 1. And all of these codes meet both of the Hoffman codes definition, okay? So it's most frequent, the longer, is it? And each of the code is not the prefix of the other code, so it's immediately decodable, is it? So if you have the code file look like this, is it? So how do we build the Hoffman tree? So how do we build the Hoffman tree? Okay, so let's see. Not here, use this. Okay, then let's see, how do we build a Hoffman tree? So build the Hoffman tree, then the case is we start from the root node. From root node, okay. So in this case, we are going to do top down. Top down building. Okay, top down. Okay, so the tree basically is later on can be used for the decoding, okay, for the decoding. So let's see. So in this case, okay, the first, okay, you have a letter, is it? And then it's code, is it? It's code. So we are going to start with the code, is it? The code is 0, okay. If it's 0, then that means it should go to, you remember our double tree should go to left, is it? So then what you can put within the node is just some asterisk, some special letters, is it? And then it's go to the left, okay, it's 0, is it? And next is what? It's 0, is it? Okay, so that means it's going to go to the left. And it's not the end yet, so you let it go to the left. And next it's 0, so it should go to left. Then next is 0, it's go to, so we have 0 and then we have 0, is it? 0, is it? So we follow the code. If it's 0, you go to the left and you just add some special letter for the node, is it? And now it's reached the end of the code, is it? So then you just add your letter as the leaf node. Okay, so it's going to be B. Okay, so now we get this part finished. And then let's see, C. Is it? Okay, see it's 0, 0, 0. And then from here it says what? 1, is it? So you let it go to right. So this is letter C. Then you record it. It's 1. Is it? And then let's see D. Okay. Okay, D is 0, 0, and then 1. So it should go to here. Is it D? It's 1. Is it? And then A is what? 0, 1. Okay, A is 0, 1. So starting from here, go to the right. So that's A, is it? And E is just 1. Okay, E is 1, is it? So now you have this tree built, is it? So we are going to code this tree, is it? And the concept is kind of like a binary search tree, is that you can build this tree, store it, is it? Store it. So that's the point is the first thing is you need to build Hoffman tree. So we build the Hoffman tree, is it, using the code file, is it, or whatever the code map you have, is it, then you can build the tree, is it? Okay, you build the tree. After we build the tree, then you may ask, what's the purpose for this? Is it, what's the purpose for this? So let's see. So then the idea is, okay, then I have something looks like this. Then I have something like this. Suppose I have 0 and then 0, 1, then 0, 0, 0, 0. Okay, I have 0, 0, 0, 1. Is it? So you get this secret message kind of thing. Is it? So this is called some message. Someone send you this message. Is it? That's how encoding and decoding works. Is it? You get this message and then you want to know what does it mean? Is it? So we need to decode it. Is it? Decode it. How do we decode it? Okay, you just, okay, it's 1. Is it? Okay, 1, then you find, oh, you go to right. Is it? So it's 1, then you follow this tree, then you go to right. Is it? You find, oh, it's E. It's E. Is it? And then you read the next, oh, it's 0, I should go to left. Is it? Left, it's not, doesn't give you anything, just an asterisk. Is it? So you keep doing, keep reading, it's right. Oh, you find it's leaf node. Is it? You have letter A. Then you have letter A. Is it? And then you keep doing, it's at 0, okay, not to stop. 0, not to stop. And 0, not stop. And 0. Oh, you found the leaf node. It's B. Is it? Then you decode this as B. Is it? And then you keep doing. Is it 0? Okay, 0, follow. And 0, you follow. And 1, oh, you find the leaf node. Is it? Okay, so this is going to be letter D. Oh, no, not D. This is going to be C. Is it? So yeah, this secret message, you see, then you can decode it. Basically, it's E, A, B, C. Is it? So if you receive this code, if you have this corresponding Hoffman tree, then you can decode it. Is it? You can decode it. Yeah. So this is how we are going to use our Hoffman tree to do the decoding. Okay. So today we get to the concept of the Hoffman tree also clear. So, and I think we run out of time. So what tomorrow we are going to see is how do we do the Hoffman trees encoding, decoding, okay? So that's all for today. And do you have any